Today's lesson is going to be about implicit differentiation. So the learning outcome for this lesson is going to be to calculate and interpret dy dx when y is given as an implied or an implicit function. We're going to be providing that as typically as an equation involving both variables x and y, and we want to determine special properties of the curve given by the following equations. So we want to be able to determine where the tangent line is horizontal, we want to be able to determine where the points where the tangent line is vertical, and we want to be able to find the points where the tangent line is undefined. So in order to master these outcomes, we need to understand a few things about what we mean by an implicit function. So up to this point, every function that we've ever seen has always been defined explicitly as a function of x, or as a function of one variable. So for example, we would see something like this: y equals the sine of 3 times the sine of x plus 17 e to the x equals 12. So notice how y is on one side of the equation, and y could also be f of x, g of x, the name of the function. And then on the other side of the equation, the only variable we see here is x. A function is called implicit if it's not explicitly solved for x, or another way of saying that, if the x's and y's, or whichever other variable you're working with, are all mixed together. So an example would be x cubed minus 3xy plus y cubed equals 0. This would be an implicit function because we can see here that the variables are mixed together, but more importantly, sometimes you're not going to be able to solve this for y. Algebraically, we could never do that to use our traditional derivative rules. So there is a way we can actually differentiate this the way that it is. And then since the equation is implicit, most times the derivative will be implicit, meaning that when we solve for our final derivative, you will see x's and y's in the derivative function. When y is implicitly is an implicit function of x, right, we're going to use implicit differentiation. And so to get started, and I'm going to make a couple modifications because you actually have a few choices here, right? Some people take all the y's in the equations and name them f of x, and they do that because they like to be able to see that, oh, I'm actually taking the derivative of a function, and so I'm really applying the chain rule everywhere I see a y. When you take the derivative with respect to x, every time where you see an x, you would just take the derivative in the normal way, but everywhere you see an f of x, you would write it as f prime of x. So another way, and then this step says, well, then unsub and put y back in. So another thing you can do is you can leave the y's in, right? But when you take the derivative, you take it with respect to y, right? So this would be the equivalent of taking the derivative of the outside function. And then you multiply the result by dy dx. This would be representative of the inside function. So personally, I like this notation because I can see where I'm applying the chain rule. It's not always intuitive to people sometimes when they're doing the chain rule, when they're trying to take the derivative of a function in terms of f of x. So this is really just a personal preference, and I will go over both methods in class with the same problem so you can kind of see the difference in the notation. So one thing to keep in mind is an explicit function can always be written implicitly. So going back to the example we saw on the previous page, right, we had y equals this equation. Well, if all I do is move y to the other side, and now everything is set equal to 0, you now technically have an implicit function. But it doesn't work the other way. Not all implicit functions can be solved and written explicitly. And so we kind of talked about that here. Like algebraically, you could never solve this for y. Because your equation involves an x and y, your derivative will usually have an x and a y. So that means if we want to find the tangent slope, we're used to just plugging in the x value into the derivative. Now we have to know the x and y value at that location if our derivative contains both variables. And then sometimes we're going to ask you to calculate the second derivative. So in terms of our dy dx notation, this is what that would look like. D squared of y means second derivative of y, the name of our function, with respect to x squared is right? Every time we take the derivative, we divide by that x. We've talked about this in the units of x. So dy dx is the first derivative. D squared y over dx squared indicates the second derivative, right? You're also f prime of x, right? We write as dy dx. So f double prime of x is d squared y over dx squared. It is possible that sometimes when you take the second derivative, the original equation reappears and you can simplify it quite nicely. That doesn't always happen. So in general, we tell you not to try to simplify things too much unless there's a specific reason, like we ask further parts to the questions.